Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
How can a tiny pen carry enough ink to draw a line more than 2 kilometers long without leaking into your pocket? The surprising answer is not simply thick ink. Pen ink is an engineered fluid designed to behave in two opposite ways. Inside the refill, it must resist leaking and drying. But the moment the microscopic ball begins rotating, the ink must flow smoothly and produce a uniform line. Achieving this balance requires industrial chemistry, precision milling, fluid mechanics, and some extremely strict quality control. Today, let us enter an ink manufacturing plant and discover the science behind the mass production of pen ink. Before entering the factory, we must understand that every pen does not use the same type of ink. Traditional ballpoint ink is generally oil or solvent-based. It is thick, slow-moving, and designed for long writing distance with minimum leakage. Gel ink is usually water-based and contains fine pigment particles suspended inside a gel structure. It produces darker, brighter lines and requires less writing pressure. Rollerball and fountain pen inks are much thinner. They flow mainly through narrow channels using capillary action. In this video, we will focus mainly on ballpoint and gel ink, the two formulations most commonly produced for modern disposable and refillable pens. A typical pen ink contains 4 major groups of ingredients. First is the carrier, the liquid portion of the ink. Oil-based ballpoint inks may use high-boiling alcohols or glycol-based solvents. Gel inks mainly use purified water combined with humectants such as glycols, which slow down evaporation. Second is the colorant. Dyes dissolve completely in the carrier, creating strong and transparent colors. Pigments, however, do not dissolve. They remain as extremely small solid particles suspended throughout the liquid. Third comes the resin or binder. It helps the color attach to paper, improves durability, and controls the body of the ink. Finally, small quantities of performance additives are included. These may control viscosity, surface tension, lubrication, corrosion, microbial growth, pigment settling, and drying. Changing even a fraction of 1% can affect whether the pen writes smoothly or fails completely. The most important science in modern pen ink is rheology, the study of how materials flow. Many gel inks are shear-thinning fluids. When the pen is stationary, the ink has a relatively high viscosity. This helps prevent leakage and keeps pigment particles from settling. But when the ball rotates, it creates shear forces inside the narrow gap between the ball and its socket. These forces temporarily reduce the viscosity, allowing the ink to flow around the ball. When writing stops, the internal gel structure rebuilds and the ink becomes thick again. It behaves almost like tomato ketchup, difficult to move while resting, but much easier to flow after force is applied. However, pen ink must perform this transformation thousands of times with far greater precision. Industrial production begins with controlled raw material dosing. Every solvent, resin, dye, and additive is checked for purity, moisture content, color strength, and batch identity. The production recipe is stored in a computerized batch control system. Load cells beneath the mixing vessel measure each ingredient as it enters. This is critical because excessive solvent may cause leakage and slow drying, while too much resin can make the ink sticky and difficult to deliver through the pen tip. Once the quantities are confirmed, the main carrier is transferred into a closed mixing vessel. Inside the vessel, an industrial agitator begins circulating the carrier. For oil-based ink, the resin is gradually added and dissolved. The vessel may be gently heated through its outer jacket to accelerate dissolution, while temperature is carefully controlled to prevent solvent loss or chemical degradation. Next, dyes or pigment concentrates are introduced. If soluble dyes are used, the process is mainly one of controlled dissolution. Pigments create a much more difficult engineering challenge. Individual particles naturally attract one another and form larger clusters called agglomerates. If these clusters enter the pen tip, they can block the microscopic ink passage and produce skipping, pale lines, or complete pen failure. The pigment must therefore pass through a dispersion process. A high-speed disperser first breaks large pigment clusters apart and wets every particle with a liquid carrier. For finer processing, the mixture may then enter a bead mill. Inside this machine, thousands of tiny ceramic or glass beads collide with the pigment agglomerates. These repeated impacts reduce the clusters to microscopic, or in some formulations, submicron sizes. Dispersants coat the particles and prevent them from joining together again. Particle size is extremely important. The particles must remain far smaller than the clearances inside the pen tip. Otherwise, even a visually perfect batch of ink could clog the pen after only a few meters of writing. After dispersion comes the letdown stage. Additional carrier, resin, and performance additives are blended into the concentrated color base until the final formulation is achieved. Technicians measure the shade using a spectrophotometer rather than depending only on the human eye. Viscosity is checked using a rotational viscometer at different shear rates. Engineers also measure density, surface tension, pH for water-based inks, and pigment distribution stability. If the ink is too thick, the pen may skip. If it is too thin, it may leak, bleed through paper, or form unwanted blobs. The acceptable operating window can be surprisingly narrow. The finished ink is now filtered to remove dust, oversized particles, and any remaining agglomerates. But there is another invisible contaminant: air. High-speed mixing can trap microscopic bubbles inside the ink. If one of these bubbles reaches the pen tip, it can temporarily interrupt the ink supply and create a blank section in the written line. The ink is therefore deaerated, often under vacuum, before being transferred to a clean holding tank. Only after filtration and air removal is the batch ready for filling. On the filling line, precision pumps inject a measured quantity of ink into each refill tube. Traditional oil-based ballpoint ink is thick enough to remain inside the narrow reservoir. Many gel refills also receive an ink follower, a clear or colored gel plug placed behind the ink. It prevents evaporation, keeps air away, and helps the ink column move toward the tip. The refill is then connected to the metal writing tip, sealed and assembled into the pen body, but the pen is still not ready for sale. Samples from every production batch are installed in automated writing machines. These machines write continuous lines under controlled speed, pressure, and angle. Engineers monitor starting performance, line continuity, color density, and the amount of ink deposited over a measured distance. Pens may also undergo hot and cold storage, tip-down leakage tests, drop tests, drying tests, and long-term aging. For documentary-grade ballpoint pens, additional testing can evaluate resistance to water, light, chemicals, and attempts to erase the writing. A batch may look perfectly normal inside the mixing tank, yet fail because of tiny changes in viscosity, pigment stability, or interaction with the pen tip. This is why the ink and the mechanical tip must be developed as a single system. A ballpoint pen appears simple, but every line it produces is the result of carefully controlled chemistry. The carrier controls movement and drying. The resin creates adhesion. Microscopic pigments produce color. Rheology modifiers decide when the ink should remain still and when it should flow. The rotating ball then acts as a miniature pump, valve, and printing roller, all at the same time. So the next time a pen creates a smooth, uninterrupted line, remember, you are not simply watching ink leave a tube. You are watching a mass-produced chemical system perform fluid engineering at the tip of your fingers. This is SimpleGAN, where everyday objects reveal extraordinary engineering.